Hi folks, this is tutorial number 30 in the playlist which is called Dynamic Scenario Animation and Simulation for 3D Experience. It's another example of a case where I have to specify initial velocity in a dynamic problem. In tutorial 29, I looked at a single degree of freedom, which is a mass spring system. But here, the situation is a little bit different in the sense that we have a block sitting on a surface, and there's friction between the two, and you give the block an initial velocity. Obviously, the block starts moving to the right in this case, and but it will decelerate because of the friction uh, acting on the block. Okay, so that's the problem that we want to model. Okay, in here we have to model it. We have to model it by activating gravity, friction coefficient, and contact between the surfaces. And we also have to use the design table in order to uh, do what we want. Now, let's look at the numbers here. So suppose that the mass of the block is 10 kilogram. We give it a kick with a hammer, and that's an impulsive force, and that gives the block an initial velocity, and it moves to the right. Now, uh, what we have to use in order to calculate the initial velocity, we're going to use the impulse momentum equation. So the change in momentum, which is mass times the velocity after the impact, minus mass times the velocity before the impact, which obviously is zero, uh, is equal to the impulse, which is the integral of the force exerted by the hammer on the block dt. Now, for small duration impact, such as what we have here, this can be approximated with a force, a magnitude of the force, some kind of force amplitude times delta t. That's called an impulse. Now, when you equate these, you can actually calculate the or estimate the value of V naught. The product of F delta t is called an impulse, and it's represented by F hat here. So basically, initial velocity is calculated according to this formula. This is assuming that short duration values, short duration impulsive force. Now, so initial velocity is approximated through the impulse divided by the mass of the block. Now, these are the numbers that I'm going to give it. So I have to model it based on these values. And let's move on. Of course, if you do F delta t divided by m, you're going to get uh, initial velocity of 1 meter per second. Obviously, because of friction, as it goes to the right, the value of the velocity decreases. There is a deceleration value of the initial velocity is going to decrease. We'll see that. Now, I want to get the analytical solution to this problem. It's a first-year dynamic problem. Sum of all the forces equal to mass times acceleration. The only force that's acting is actually the friction force. Mass times acceleration equal to negative friction force. And if you divide by m, you're going to get the constant acceleration, which is actually constant deceleration, which is the coefficient of friction, kinetic friction times g. Uh, and if you integrate this thing twice, you're going to get the position of the block along the track. If obviously derivative of that is going to give you the velocity of the block as time goes on, and you can see that because of this minus mu g times t, velocity decreases. And then for the numbers that I have, s is going to be right there, and velocity is going to be right here. Initial velocity, notice that when t is 0, initial velocity is 1. And as time goes on, that one decreases. And the acceleration is obviously this minus mu g. So these are the numbers, particularly this acceleration, is what we're going to be comparing our calculations against. Now, a couple of things. We have to apply an impulsive force. In other words, somehow I have to tell the software that if time is less than 0.01, then here's the value of the force. After that, drop the force to 0. The problem is that if this was a constant throughout simulation, no problem. I've done many problems like that. If it can be given by formula, there's no problem. But if there is an if statement involved, such as the case that we have, the rule which is supposed to work, unfortunately, it does not. The rule is writing a few lines of code involving uh, if statement. That does not work, or I don't know how to do it. However, that's doable by giving that information in terms of a design table, in terms of design table. And that's exactly what we're going to do. And that's how it was done in tutorial 29 and a few ones that were done earlier with design table. Now, we cannot use a prismatic joint here because it is actually moving along a straight line, you know that. But prismatic joint cannot be used because when you use a prismatic joint, the contact pressure between the two surfaces is going to be ignored, and therefore friction becomes meaningless. Okay, so what we have to use is activate gravity, define contact, use a force excitation through the design table. Force excitation is basically, uh, you know, saying that if time is less than this, here's the value of force. If time is bigger than that, force is zero. However, I told you that we can't do it, I couldn't do it based on a rule, writing a few lines of C code, so I have to do it with design table. These are the dimensions that I'm going to be using for our problem. They're totally kind of irrelevant because I'm going to define the mass of this block independently of what its size is. And of course, the ground is stationary. And I'm going to apply my impulsive force at the center of this block, center of gravity of this block. Now, let me remind you, because we have to use design table, what needs to be done, you go to the tools, design table, and it says, do you want to create one or do you have one? We want to create a second radio button. And then it says, okay, in that design table, the two columns, what do you want to put? Well, I want to put the force versus time. So these two are going to go to the right-hand side. You have done several of these problems before, so including 29. And then it says, okay, I'm going to create it. And then when the Excel spreadsheet is created, you go and put this information. This information is exactly what I had for time less than 0.01 is 1,000. At 0.01 is 1,000. And immediately after that, it's going to drop to zero. Okay. Now notice that when you do that using design table, in the force law excitation dialog box, you get this design table icon here, right there. Okay, so now I'm going to run this thing with the symplectic Euler, and it's going to give you better comparison with the analytical solution. And let me remind you that we have to, when you define contact, uh, if you're using the symplectic Euler, it's this second tab right here, symplectic Euler right there. This second tab, you activate it and put the proper uh, coefficient of friction here, 0.01. If you're using the DASSL, then it's the first tab, and then you put the 0.01 as a friction coefficient. The one with symplectic Euler is going to be closer when compared to uh, the DASSL. Okay, let's go ahead and do that. Let me insert the ground first. Right click, insert 3D part. I'm going to call that thing ground. Right click, properties, ground and ground. It's the ground. And here is the part name, ground. Okay, let's go ahead and make that. It's just a long box basically. I'll double click on that. All right, I'm in part design, so on that vertical plane, I will sketch a box, this box, okay, the yellow one. Let me see now. Let me make a rectangle here, and we're going to dimension it. My units are already set to meters and things like that. I want this length to be 2.5 meter, 2.5 meter, and this height, although it really doesn't matter, but I want to make it look good. So I'm going to make it 0.05 probably, 0.05. Let's see what it looks like. Yeah, okay, that's good. Exit, and then we're going to pad it. We're going to pad this thing symmetrically. Oh, well, we're going to pad it by, it looks like 0.1. Okay, 0.1 meter. Yeah, 0.1 meter. There's the profile. Good. And I'm going to change the color of this to yellow. Okay, that takes care of the ground. 2.5 meter long, and that's pretty much it. You go all the way to the top and insert the block. Insert the 3D part. Okay, call it block. Properties, block, and block. Okay, let's go make it. Double click on a convenient plane, on that vertical plane. I'll sketch a rectangle which is 0.1 meter by 0.1 meter. Right there. 0.1. Okay, and this is also 0.1. All right, exit. And we're going to pad it by the same length, which I believe it was 0.1. Yeah, 0.1. Good. Now, let me change the color of this. Right-click properties. I'm going to change the color of that to orange. Cosmetic reasons. And I'm going to create a point at the centroid. While I'm in this block, I'm going to create a point exactly at the center of gravity or centroid of that block of this pad right there. So notice that a point has been created right there. There's an X there. You can see that right there. Okay, good. As far as the model is concerned, we're pretty much it. However, why don't we do some, let's go all the way to the top and notice that here I can fix, well, we're gonna apply our fixed part, which is this ground later on. Okay, so let's go and apply the masses on this thing. So we go to 3D mechanical systems design. This is where we define the mass of these things. If you scroll all the way to the right, there is a weight. All the way to the. Oh, click on the mechanical systems tab and go all the way to the right. There's a weight definition, which is a misnomer. Actually, it should be mass. But anyway, weight definition. Notice that they're both red, which means because we haven't done anything. If you look at the ground, there is the ground. You click on it, and then it says declare the mass of that or the weight of that. Click on that link, and what I'm going to do is I'm going to click on that checkbox. That means that the properties of steel are going to be used for this ground, but that's totally irrelevant because the ground does not move. So, but that's fine. So notice that it turned blue, which means that the property is defined. And I do the same thing for the block. Again, click on the hyperlink, put properties of steel on it, but then I'm going to change that thing to be actually, let me go back here. Okay. Oh, try it again. Click on that. And now, okay, I see. Let me move this thing out of the way. You know why I couldn't see that? Because the box was opening on the left side momentarily. Let me click on this. Oh, right there. I couldn't see this. That's why I had to go and do it again. Look, 10 kilogram. Okay, there, 10 kilogram. You can see that. When I was trying to change it, the box would open over there. I couldn't see that. See that right there. Anyway, we declared the proper masses. 10 kilogram for the block, and for the ground it doesn't matter. So close that. Now, what we're going to do is, first of all, we're going to create. We're going to fix the ground. So here are the engineering connections. Let's see if we can find it. Uh, engineering connection. Okay, so I guess we're going to go to the assembly. Going to go to the assembly, engineering connections, fix the ground. Ground is fixed right there. See that? Now, I'm not going to create a prismatic joint because it's not going to work. So we need to do create contact. See contact connection? Group 1, select the block right there. See that? For group 2, select the ground and say OK. So we have defined block and the ground, contact between them. Now, there are two tabs here. Since we're going to be using both of them, for example, this is the tab associated with the symplectic oiler. I'm going to put a coefficient of 0.01 here as coefficient of friction. You're going to need this number if you use symplectic oiler. And since I'm going to also try DASSL, I'm going to click on that tab and put also 0.01. Okay, remember, if you're using DASSL, it uses this information. If you're using the symplectic oiler, it uses the stuff in the second tab, this tab. But anyway, I changed them. Good. So we created our contact here with the proper values. Now, let's go and create our, this gravity is not going to work here. We have to do that later. Mechanism representation. All right. Mechanism manager. Notice that we have a fixed part and a contact. Good. Close that. All right. That's pretty much it. So then we're going to go to mechanical systems experience. This is fine. Say OK. We already have our mechanism. Okay, you can see that we already had our mechanism. I did not have to do that. Now, first of all, I'm going to put a probe at that location. So where is the probe? Probe here. So click on scenario, select the position and speed accelerometer probe. I'm going to put it right at that location because we're going to be plotting stuff for that location. Then we're going to do the force excitation, force law excitation. You click on that. Okay, for the support is this block. For the point of application is that point. For the direction is along the length of the block. I'm going to reverse this thing because I'm going to push it to the right. Notice that it puts a 1 here, but it doesn't matter. We're going to change that with the design table. We say OK. So you notice that the excitation has been created right there. But I told you how to do the design table. If you go back here, you have to go to Tools tab. So there's the Tools tab. You scroll all the way to the right until you come across that design table right there. See, that's what this is doing. You click on it. It says second radio button. We use the second radio button. It says, what do you want to put in that design table? I want to put the time and I want to put the force. I say OK. Just say yes. So the design, and then this is the name of the design table, default name I'm choosing. It says Excel spreadsheet basically. Wait a minute. Okay, right here. Now I want to edit the table. All right, and remember what I need to do is to put this stuff in it. 0, 1,000, 0.01, 1,000, and slightly above 0.01, 0, drop to 0. So let's go back here, edit table. This is going to be 1,000, not 1, at 0.01 second. This is going to be also 1,000. That's slightly above that, 0.0111, 0. And then make sure you save this thing. Make sure you save it, assuming there were no typos here. And then you can close it. And it's going to give you that the message that the table is going to be synchronized with the model. We say fine. And then we say OK. Notice that when you do that, design table is created. And if you double click on the force excitation, there is a, see that? There's a design table icon. So what I'm showing you now is this. Okay, good. And then we close it. Now, gravity. Don't forget the gravity. Here's the gravity. Gravity excitation. Gravity excitation. You click on it. Minus 9.81 in the negative z direction. So we have two excitations here. One is the force. The other one is gravity. All right. And there's a probe here. You can see that. There's a probe there. And now we're going to go and create our dynamic scenario right there, dynamic scenario. Force law excitation was created, we put it in. Gravity excitation created, we added. Under the probe, remember at that location I created the probe. And for the parameters, first of all, I'm going to run it with symplectic Euler. And let's see what I have here. I use the same information here. The only thing that I've done here is 3 seconds, right? 3 seconds. Let's go here, 3 seconds, and say OK. Don't forget to save. And then we're going to run. Give it a minute. Okay. So put the cursor here, right click, run it. So what happens? This goes and then it falls eventually off the off the track because 3 second make it go past that point. Now we go to the view scenario results. Deselect everything. First of all, let's look at the force in the y direction. Notice that it was 1,000 and then drops to 0. That's good. Uncheck that. Let's look at the velocity, velocity in the y direction, linear velocity in the y direction. Notice that the velocity drops, and it drops according to this linear function, And we look at the acceleration, we should have minus 0.0981 inch-ish. Okay, so go there, unselect that, and look at the linear acceleration in y direction. Now this doesn't show because the acceleration initially was very high because of that impulse, okay, and then it drops. If you go to the table, you can see that you're going to get minus 0.098. That matches this, okay. Now, of course, if you go further down until it falls off the track, you get all zeros right here. Okay, good. So let me close this. Now what I'm going to do is I'm going to go to scenario, double click on it, and change this thing to DASSL. Okay, and then again run it for 3 seconds. I'll run it. And then we're going to check our answers. It's going to fall off the track. Okay, let's go and check our answers. Go here. deselect all. Let's look at our velocity is going to be probably okay. Uh, Linear velocity, as far as at least the shape is concerned, it's okay. Remember, this piece is where it falls off the ground. And then acceleration. Uh, yeah, if you look at the table, you see the numbers are not very far off, generally speaking, from 0.0981, but it's all over the place, but not very far from it. Now, what happens if I make the coefficient of friction 0? For example, remember, I'm using DASSL here, right? Remember, I'm using this. Let's go back there. In fact, let me change this thing back to the uh, symplectic Euler. Okay, and then I'm going to go and change the coefficient of friction equal to 0, no friction whatsoever. So I go to the contact here, double click, one time. For this second tab, instead of kinetic coefficient of friction being 0.01, I'm going to make it 0, no friction. And let's see what the effect is going to be. No. All right, let's go run it. Obviously, no friction. It's going to go faster. Higher acceleration. It's going to fall off. But let's look at our velocity. Let's look at our velocity. Our velocity, select all, velocity in the y direction is going to be constant. That doesn't surprise you. That does not surprise you. Because, by the way, this has to be 1. This has to be 1. But, and the acceleration, where is that? Linear acceleration is going to be 0. Yeah, because there is no friction. There's nothing to decelerate. So that takes care of this tutorial. The moral of the story is that if you have to do initial condition for velocity, to the best of my knowledge, there is no way of directly doing it using the icons and the functionalities that are available here. I gave 2 problems where I did that based on defining an impulsive force, and then that impulse turns into initial velocity, and then these are tutorials 29 and 30, which is just it. All right, folks, good luck.